In this lecture, let us discuss the decimal adder. So till now we have seen the binary adders, especially half adder and then full adders. So these are all binary adders. Now we would like to see how to add decimal numbers. So if you take computers or calculators, the input is not binary, right? So the input is in the form of decimal. So the computers or calculators that perform arithmetic operations directly in the decimal number system. Okay, so if you feed the input like decimal, but in turn what happens is this decimal is converted into binary and it does all the operation like addition or subtraction or whatever it is, and then again it converts back into, it does the operation and then again convert back into decimal. For example, if you want to add two numbers, let's say 4 plus 5, then the answer is 9. So what you do, this 4 is converted into binary like 0 1 0 0 and this 5 is 0 1 0 1, right? So then you add these two numbers and again convert back to binary decimal like 1 0 0 1. So this is equal to 9. That's how it does the function. An adder, for such a computer must employ some arithmetic circuits. For example, half adder or full adder. So this circuit accepts the input in the binary form and does the addition, and then it produces the output. For example, for binary addition, when I say binary addition, it is sufficient to consider a pair of significant bits, right? Only have two inputs. Let's say this is A and this is B and the output is C, and let's say this is sum and there is a carrier. So one is addend and the other one is augend. So there are two numbers and those two numbers you add it and get the output in the binary number system. But a decimal adder requires minimum of 9 inputs. Why? See, in the binary adder I need only two inputs, right? Only two inputs. But in the case of decimal adder, what do we mean by decimal adder? I have two decimal numbers. So before that, the decimal number starts from 0, 1, 2, 3 and goes all the way up to 9. So I am giving two numbers. Let's say one is 2 and another one is 3. So there are two inputs. These two inputs are in decimal, but the inside the block, the operation is done in the binary. Therefore, you represent this guy in the form of binary. So how many bits do I need? 3 bits or 2 bits or 4 bits? I need 4 bits. Why? Because for 9 I need 4 bits, 1 0 0 1. For 8 I need again 4 bits, 1 0 0 0, and 7 0. For 7 I need only 3 bits, but anyway 8 and 9 needs 4 bits, so I'm going to use 4 bits to represent the decimal numbers. So let me write it down here. 0 1 2 3 4 5 6 7 8 and 9. These are my decimal numbers. 0 you represent 0 0 4 zeros, 0 0 0 1, 0 0 1 0, 0 0 1 1, and then 0 1 0 0, 1 0 1 0. I'm sorry, this is 0 1 0 1, then 0 1 1 0, 0 triple 1, 1 0 0 and 1 0 1. And one more name is there for this 8421 code. Why is it 8421 code? The weightage is 8421. For example, you take any one code, pick it up randomly. This one 0110, and this is the 8. The weightage of this position is 8, and this guy has 4, and this guy has 2, and this guy has 1. Now 8 times 0, 0, plus 4 times 1, plus 2 times 1, plus 1 times 0. Now if you add all those things, then you'll get 6. So this is basically 6. That's what we mean by 8421 code. You take this guy 1001, here 8421, so 8 plus 0 plus 0 plus 1, which is 9. So by the way, this representation is called 8421 code. So for decimal numbers, I need minimum 4 bits. Therefore, to represent this, I need 4 bits. To represent this input, I need another 4 bits. So 4 plus 4, I need 8 bits. And if you want to carry from the previous bit, then something is called carry in. So one more bit. So you take 1. So totally I need 9 inputs. Okay. So a decimal adder requires a minimum of 9 inputs. And what about the output? I need 5 outputs. Suppose if you add this 2 plus 3, the output is 5. So again, to represent this 5, I need 4 digits like 0, 1, 0, 1. So 4. If there is a carry, then I need one more bit, extra bit. So 5 outputs. Okay. See, 4 bits are required to code each decimal digit, and this one is carry out. So there is a wide variety of possible decimal adder circuits depending upon the code used to represent the decimal digits. And here, as I said, we are going to use BCD code, binary coded decimal. BCD means binary coded decimal representation. Let me write it down. BCD, binary coded decimal. Okay. So in the input I need 9 bits, and in the output I need 5 bits. Okay. Now let us see the BCD adder, how the numbers are added. So before we enter into the circuit diagram, let us look at some preliminary. Okay. So let us consider the arithmetic addition of 2 decimal digits which is in BCD form. Okay. So as I said, my BCD numbers are 0, 1, 2, 3 up to 9, and I want to add 2 decimal number. So the minimum is 0 and the maximum is 9. So I can pick it up any one number from here. So I can add 0 plus 0, I can get 0, or 0 plus 1, I can 1, 0 plus 2, 2, like that. I can put all the combinations. And suppose in case if I take 9 plus 2, then what? 9 plus 1 if I take, then this is going to be 0, and 1 is a carry. Actually the answer is 10, but again I can break this into 2. The 0 is the sum and 1 is the carry. So whatever you do in the input side, the output again falls in this set, right? So whenever the input exceeds 9, the output sum cannot be, whenever the input exceeds 9, the output can be more than 9. So it can be 10, it can be 11, it can be 12, and it goes all the way up to maximum how much? 19. Because here the maximum number is 9, and you put one more 9 plus, then 18. Maybe if you take one carry input from the previous bit, then if you add 1, so maximum is 19, right? So you have BCD adder, you have addend and augend. You can give any one digit, 0, 1, 2, anything you can give. And here also you can give any one thing, and there is an input carry from the previous bit. Okay, so the maximum I can give in this position is I can give 9, and here also I can give 9, and this can be either 1 or 0. Okay, the previous carry. So if it is 1, then it is going to be 19. So it cannot exceed 19. The output, you take BCD adder, the output cannot exceed, cannot be greater than 19. So if you write 19, then this 1 is the carry out, and 9 is the sum. Okay, suppose we apply 2 BCD digits to a 4-bit binary adder. So you have a binary adder. I think you already studied this. Okay, you take a full adder, 4 full adders, right? So I have drawn in the compact form. So I have 4 inputs and the carry, this carry in. Okay, so there are 4 input bits. You take one more binary adder. Okay, 4 input binary adders. So I have drawn little wrongly. Let me draw it correctly. Like this. And this 4 bits represent decimal number A, and you put another 4 inputs, and this represents decimal number B. So the output is A plus B, and this A plus B will give you the sum here, and then you put the carry here, carry out. Okay, so the adder will form the sum in binary and produce a result that range from 0 through 19. Okay, so let me write down all the combinations here in the form of table. So I have binary sum. So see, for example, if you add 2 numbers, let's say 0 plus 0, so the output is 0. So how do you represent the 0? 0, 0, 0, 0, 4 zeros. So I may have 0, 0, 0, 0, 4 zeros. Let me call these numbers z suffix 1, z suffix 2, z suffix 4, z suffix 8, 8421 code. If there is a carry, then let me write down this carry, let me denote this carry as k. Now there is no carry here, carry, output carry, so this is the 0. If you add 0 plus 1, then you will get 1. 1 you can represent 0, 0, 0, 1. So 0, 0, 0, 1. And then 1 plus 1, it is 2. 2 is 0, 0, 1, 0. Like this you can keep on fill it up. So 0, 0, 1, 0, 0, 1, 0. Again the carry is 0, output carry is 0. Then 0, 0, 1, 1. Then 0, 1, 0, 0. Then 0, 1, 0, 1, and then 0, 1, 1, 0, 0, 1, 1, 1, 1, 0, 0, 0, and here everything is 0. These are some combinations of binary. For example, what is this 9? This is 9, right? How do you get this 9? 9 you can get it as like 4 plus 5 or 8 plus 1 or 7 plus 2, whatever the combinations you can take it, but finally you will end up with this one 9, 1, 0, 0, 0. Okay, now the moment you exceed 9, then there is a problem. Okay, for example, if you want to add 5 plus 5, so the binary adder, you take 4-bit binary adders, binary adder. So here 4 bits, let's say 0, 1, 0, 1, right? That is 5. And then here also you give 0, 1, 0, 1, 0, 1. The output is 1, 0, 1, 0. There are 4 outputs. 1, 0, 1, 0, like that. And of course, the output carry is 0. So So it is going to be 1 0 1 0 and this is 0, but in decimal number representation this is not there. Our decimal number starts from 0 1 2 3 and goes all the way up to 9, but we don't have any equivalent number in number for 1 0 1 0. So what shall I do it? So there is a problem. So let us write down the combination. So then we will think about what we can do about that. So my decimal numbers, if you add two decimal number, I may get 0, I may get 1, I may get 2, 3, 4, 5, 6, 7, 8, 9. I will get 10 also. 11, 12, 13, 14, 15, 16, 17, 18, 19. That's it. Because I am adding two decimal numbers. If you add two decimal numbers, the result cannot exceed 18. Okay, so if you take two decimal numbers A and B, A can take maximum of 9, B can take maximum of 9. I am talking about two decimal numbers. So 9 plus 9, it is 18. If you consider the previous carry, then you add one more, so 19. So therefore when you add two decimal numbers, the result cannot exceed 19. So that's why I stopped at 19. Okay, so therefore 9, what did I do? I'm sorry, I have done something somewhere wrong. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. I'm sorry, I wrote it wrongly. This is 1 0 0 1 and then 1 0 1 0. Then just to fill it up this combination, this is 0, no carry. Then 1 0 1 1, 1 1 0 0, 1 1 0 1, 1 1 1 0. This all are ones, and here the carry bit is 0. The moment you exceed 15, then it becomes 0 0 0, and here the output carry is 1. Then again 0 0 1, then again the carry is 1, output carry is 1. 0 1 0, 0 0 1 1. That's it. So these are all my combinations output. Now up to 9 there is no problem. Up to this position, no issues. Okay, but the problem arises after this 10 only, because we don't have equivalent number. We don't have equivalent number for this 1010. So what shall I do? So I need to convert this into decimal number. See, my decimal number starts from 0 and goes all the way 9, but I don't have any number for 1010. 1010 I can represent by 10 like this. But again, this is a decimal number. For this, how do you represent? 0 0 0001 and 4 zeros. So this is the binary representation for 10. If you have a 10 like this, 10 decimal number system, then this 1 can be represented in binary as 0 0 0 1, and this 0 is 4 zeros. That's it. Okay, that's how I represent the number 10 in terms of binary. But this one, how do I represent? That is a problem. Therefore, whenever the sum exceeds 9, okay, so in that case, what you do? You add 6 to that number. Okay, so 1 0 1 0, right? This is let me take 1 0 1 0. With this you add 6. Just hold on 1 second. 6, you can write it 0 1 1 0. You add it now 0 1 plus 1 1 0, so you put 0 here, carry 1, 1 plus 1 you add these two, again 0 you put 1 here, okay, and then 1 plus 1 again 0, you put 1 here. See this 4 zeros, and this 1 I can put 3 zeros in front of this, no change. So this is 1 in decimal and this is 0. So this is my decimal number system. So I started with 1010 and I added 6 to that 1010. This 1010 is the binary representation. I mean, if it is this is capital A in number system, in hexadecimal number system, this is A and then B and then C, D, E, F, like that. Okay, so this 1010 is nothing but capital A, or in the binary, I mean in the hexadecimal it is capital A. So with that you add 0110. The 0110 is nothing but 6. You add these two numbers, then you'll get this number system. So this first 40 represents this 0, and this 1 you can put 3 zeros in front of that. So this 4 digits together represent 1. So therefore decimal number 10 can be represented as 0001 and then 4 zeros. Like that you can represent. So that's what we are going to do the correction here. So whenever you add 6 to the binary sum, then it converts it to the correct BCD representation. See, this is not in the correct form. 1010 is not in the correct form. To make it correct, we added 6 to that to make the correct BCD representation. Okay, so therefore let me write down here BCD sum. So in this, let me write down carry, let's say this is carry, and then yes, sum. Okay, so let me write S suffix 8, S suffix 4, S suffix 2, S suffix 1, and this is BCD sum. And let me write down the equivalent decimal number also here. The left hand side I already wrote it. Decimal. Okay, S8, S4, S2 and S1. So 00, no change, you write all zeros as it is. 0001, 0010, 0011, 0100, 0101, 0110, then 0111, 100, and then 1001. So there is no carry. Okay, so you put all carries 0. The moment you exceed 9, then there is a problem. So you need to do the correcting factor. You add 6 to that. If you add 6 to this 1010, then it becomes, then the carry becomes 1 and then 4 zeros. Again carry becomes 1, 001, carry is 1, 0010, 10, and then 1, 0011, right, and then 1, then 0100, okay, and then this one, if you look at 10100, right, so 101, okay, and then this is 0110, and then 1. This one, if you add 6 to this, then you will get 0111, 17, okay, and this one is 18, that is 1000, and then 1, 1001. Now we can write down the corresponding decimal number. Okay, what is this? This is 9 and this one is 1, 19. 100 is 8, so 18. 011 is 7, so 17, 16. 0101 is 5, so 15. This one I can think in terms of 0001 like this, no change, and this one also I can think of 0001 like that. So this is 14, 13, 12, 11, 10. This 4 zeros corresponding to this 0 and this one corresponds to this one. And then 09, 08, 07, 06, 05, 04, 03, 02, 01, 00. That's it. That's how you do the decimal addition. Okay, so if you examine the content of the table, it becomes apparent, right, that when the binary sum is equal to or less than, no problem, the corresponding binary number is identical. See, this is binary number and BCD system, both are identical. Here also 4 zeros and here also 4 zeros, and including this 0. Here 001, 001, 0010, 0010, they are identical. So therefore there is no conversion is needed. Now the problem arises when the binary sum is greater than 9. So this is my binary sum. In this, if it is exceeds 9, then we need to do some correction, because this 1010 is an invalid BCD representation, right? 1010 is an invalid, because we don't have any decimal number to represent this 1010. Invalid representation. Invalid, I can say BCD representation. Therefore, to convert this invalid BCD representation, I need to add 6. Okay, 0110. Therefore, the binary sum is converted into the correct BCD representation. See, now this is the correct BCD representation. So from all these guys, I have added 6 to get the correct BCD representation. And also it produces the carry, output carry. So now we need to design a logic circuit that detects the necessary correction, and that can be derived from the entries of the table. For this you can put a K map and simplify the C. Okay, this is a 5 variable K map. You draw the 5 variable K map. I think you might have studied this in the previous unit. So you can draw the 5 variable K map and then find the expression for C. So if you draw the K map, 5 variable K map, and if you try to find the expression for carry, then let me write down the answer. You can do it on your own. It's very simple. So K plus Z8 Z4 plus Z8 Z2. Okay, so you need to take this K. In the K map, the inputs are K, Z8, Z4, Z2 and Z1. You know 4 variable K map, right? So 4 variable K map, right? In the similar way, you can draw this 5 variable K map and try to get the solution for C. So half of the table, not half of the table, up to 0 to 9, the entries are 0, and then 10 to 19, the entries are 1, and remaining terms are don't care terms. So you can substitute, and then finally you'll get the expression for C like this. Okay, so we need the correction whenever the input exceeds 9. Up to 9 there is no correction, they are as it is. Look at here, no change. The moment you exceed 9, we will get invalid BCD representation. These are all invalid BCD representations. Okay, these are all invalid BCD representations. So we need to do some corrections. That is why we are adding this 6. So therefore from, let me erase this. Therefore from 1 0, oh my god, okay, now 1 0 1 0, then 1 0 1 1, 1 1 0 0, 1 1 0 1, this one and up to this one. You take this, how many, 1 2 3 4 5 6 combinations. Okay, so in the 6 combinations we need to add the correction factor. Okay, and if you take this another 4, then I have 1 in this position. So whenever 1 in this kth position, then I need to look at this Z2 and Z1. Okay, therefore the condition for a correction and an output carry can be expressed by this Boolean function. So whenever the carry is 1, say this is my carry, right? This came and this carry C equal to 1 here. So carry is 1 here, carry is 1 here, carry is 1 here, carry is 1 here. Whenever the C equal to 1, it is necessary to add 0 1 1 0, that is 6 to the binary sum, and provide an output carry for the next stage. So let me draw the diagram for this implementation. So let me take a BCD adder, binary coded decimal number adder. Okay, so let me take the add end here. For add end I need 4 inputs. Let's say number A, and then I have augend here, again 4 inputs. Augend, let me say the number B. This A can be any number, 0 2, 0 1 2 up to 9, and this B also can be any number, 0 1 2 up to 9, and the previous carry in. So this is 4-bit binary adder. So the output is Z1, Z2, Z4, Z8. The subscript 8421 says weightage of the binary representation. Okay, now this K is here, output carry out. So whenever the output Z1, Z2, Z4, Z8 exceeds 1001, I need to add the correction factor. Okay, whenever it exceeds, then I should add 0110. For that I need to introduce some combinational circuit, and that circuit is done with the help of this Boolean expression K plus Z8 Z4 plus Z8 Z2. Okay, so K plus Z4, what is it, I forgot, Z8 Z4 plus Z4 Z2, sorry, Z8 Z2. So you just draw a straight line like this. So Z8 Z4, you put an AND gate, you take the line from here Z8 and then Z4, and for this Z8 Z2 put one more AND gate, then Z8 and then Z2. Okay, and K also is there, so therefore you put in the 3 input XOR gate. Sometimes you may not have 3 input OR gate. Sometimes you may not have 3 input OR gate. In that case you can use two inputs OR gate. So here let me assume that I have 3 input OR gate, and like this. So this is my output carry. So what is the purpose of this combination circuit? It does the it adds this 0 1 1 0 whenever the output exceeds 9. Okay, so again give this guy to the parallel adder. There are again 4 inputs. In this we need to add 0 1 1 0, right? So that means you connect these two guys to 0 voltage, 0, and this one, how do you get this one? You take this from here like this. That's all. And here this is S4, S2, S8, S8, S4, S2 and S1, and this is again 4-bit binary adder. That's it. And this will be 0 when Z8, Z4, Z2, Z1 is less than 9. Okay, and the output carry is 1 when Z8, Z4, Z2 and Z1 is greater than 9. So whenever the output of the first 4-bit binary adder is greater than 9, then you have to add this 0 1 1 0 to make the valid BCD representation. So that is the only purpose we are including this combinational circuit here. Okay, so therefore I have a BCD adder that adds 2 BCD digits. Let me call this is A and this is B, and the sum digit in BCD is obtained here and in this position and in this position. So the 2 decimal digits together with the carry input carry are first added with a 4-bit binary adder. Okay, and this 4-bit binary adder produces this 4-bit binary sum. Okay, when it is equal to 1, whenever the carry output is equal to 1, then the binary 0 1 1 0 is added to the binary sum through this bottom 4-bit adder, and the output carry is generated from the bottom. See, this bottom generator this guy also, this bottom 4-bit adder also produces output carry that we will neglect it. Okay, when this output is equal to 0, nothing is added, because if you look at, if this point is 0, then 0 comes here. So this point is 0, this point is 0, already these two lines are, this point is 0 here and this point also 0 here, so nothing is added. 0 plus anything is the same. But whenever it is equal to 1, then 0 1 1 0 is added to the binary sum through this bottom 4-bit binary adder. Okay, and the important point is the output carry generated from the bottom adder can be ignored. So this output carry is ignored since it supplies information already available in this point. Therefore, a decimal parallel adder, in case if you want to consider a decimal parallel adder, then what will you do? So you take this setup, okay, you take this setup for one digit. Suppose if you want to add a 94 plus 55 like this, or 54 like this, then 5 plus 4 will be added this setup, and you take one more setup like this, put it in the parallel form, so that these two digits will be added. Okay, so let me call this is x, or let me call this is y. So you have y and then x, the same setup. Okay, the same setup you put it here. So this two 4-bit binary adders are placed side by side. So let me draw a simple circuit diagram so that you will get clear understanding. Let's say let me want to add 95 plus 54. What you do? You take one 4-bit binary adder. So, and this one is, let's say 5, and then here you add 4. Okay, and then you put this AND gate and then OR gate output, all those things. Then again you put one more 4-bit adder. One, two, three, 4, 1, 2, 3, 4, right? So 95, 54. So this 5 is here and this 4 is here, and then you put 9 here. 9 is 1001, and this one is 0101, 0100, and this one is 5. Let me take 64. So 0110 like this, or let me take 74, 0111, this is 7. Now the previous carry, I don't have any carry, so this you made it 0. So it produces 4 outputs. These 4 outputs again give it to another 4-bit binary adder. This also 4-bit binary adder. You put a AND gate here, 2 AND gates. This is Z8, Z4, Z2 and Z1. Z8, Z4, and then Z8, Z1 or Z2, I don't know what is that. Z8, Z2, sorry. Z8, Z2, that's it. And put an OR gate output. So this is output of the first one. Give it to here, like this, and this one is given back to this input. Okay, and then put another 4-bit binary adder. So Okay, I'm sorry, I run out of the space here. Anyway, so let me put two AND gates, one OR gate, then you connect it here, and oh, hold on, okay, let me finish. Okay, no problem. Put like this: Z8, Z4, Z8, Z2. Okay, so this is my output carry, and this one is take this input, and here again there are 4 inputs. You have to add 0 1 1 0, right? So what you do is you take these two guys to 0, and then like this. So whenever it exceeds 9, then you add this 0 1 1 0, 6. Okay, decimal number 6 is added. Similarly, here also you take this one. There are 4 inputs. 0 1 1 0. So these two are connected to 0, and then what did I do? I'm sorry. Yes, 0 1 1 0. Okay, I did a mistake. I'm sorry. Okay, so like this, and then like this. So this is 4 outputs: S8, S4, S2, S1, and here again S8, S4, S2, S1. Now look at the operation now. Now 5 plus 4, 9. Okay, so this is 1 0 0, 1 will come, and this is 0, nothing to worry. So this 1 0 0 1 will come here, and anyway this input is 0, this input is 0, already I have here 0, and this also 0. Therefore the output is 1 0 0 1. 9. Fine, perfectly fine. Now 9 plus 7. 9 plus 7 is 16, right? So 16. So how do you represent 16? 1, then 4 zeros. So here the output will be 4 zeros, and then 1 will come here. Okay, and then 0, here also 0, this input is 0, the output is 0. And here this 2 are 0, so the output of AND gate is 0. So this input is 0, this input is 0, but this input is 1. If any one input is high, then the output is 1 in the OR gate. So this 1 will come here. So this all 4 zeros reach here 0, and here 0 1 1 0, isn't it? 0 1 1 0 plus all 4 zeros, if you add, then what will you get? 6, right? Yes. So 0 1 1 0, so 0 1 1 0, so this is 6, decimal number 6, and here decimal number 9. Fine. Now what about the output of this carry? This is 1, right? This 1 is nothing but 0 0 0 1. So my output is 0 0 0 1, and this one 0 1 1 0, and then here 1 0 0 9, 1 0 0 1. So this one is 1 in the decimal, and this one is 6 in the decimal, and this one is 9 in the decimal, 169. So 95, what did I write? 95 or 90? Sorry, 90. 95 plus 74. 74. 5 plus 4, 9. 9 plus 7, 169. That's it. I got the answer. So that's how you can implement the parallel adder. So here I have taken two decimal numbers. So you can take 3 decimal numbers, 4 decimal numbers and put them in parallel form. See this block, let me zoom in. See this whole block is parallel with this guy. You put one more parallel block here and you put one more parallel block here, you can put one more parallel block here, like that you can add a number of parallel blocks and you can construct the parallel decimal parallel adder. Therefore a decimal parallel adder that adds n number of decimal digits. So I have n number of stages. But in this case what happened, see this is my first stage and this is my second stage. So in order to get the output from the second stage, I have to wait the output from the first stage. So once I get the output from the first stage, then I can do the operation in the second stage. Therefore the second stage depends on the first stage. Okay, so the output carry from one stage must be connected to the input carry of the next order stage. See this carry is connected to the input of the next order stage. So that's how the parallel decimal adders are constructed. So whatever is happening in your computer or in the calculator is in the form of binary, but the input is decimal and all the operations are done in the binary and again you get back to decimal. Okay, in case if it is not in the proper decimal format form, then you have to do some correction factor. I mean you have to add 6. This 6 is nothing but 0, 1, 1, 0. If you do that, then you'll get back the correct decimal form. So I think let me stop here. In the next class we will continue the next topic. Thank you very much. Magnitude comparators or subtractor or any one topic we will look at it. Thank you.